The complex field. The standard form of a complex number is a plus bi, where a and b are real numbers. We use the letter C with a double-struck font for the complex numbers. So C is equal to the set of a plus bi such that a and b are real numbers. We can also write the complex number a plus bi as the ordered pair ab. In this way, we can visualize a complex number as a point in the complex plane. Here's a picture of the complex plane with some points plotted. Let's look at some examples, specifically the points that I have plotted there. The complex number 2 is an abbreviation for 2 plus 0i. As a point, we could write it as 2, 0, and we see it in the complex plane, 2 units to the right of the origin on the x-axis. The complex number I is an abbreviation for 0 plus 1i. It could also be written as the ordered pair 0, 1, or the point 0, 1. And we can visualize that in the complex plane by moving 1 unit up from the origin. The complex number 1 plus 2i can be written as a point as 1, 2. And to plot that point, we move right 1 and up 2 from the origin. The complex number 1 minus 3i is an abbreviation for 1 plus negative 3i. As a point, that is 1 comma negative 3. And to plot that point, we move to the right 1 and then down 3. The complex number negative 3 plus 2i as a point is negative 3, 2. We move left negative 3 and up 2 to plot that point. One more example, negative 1 minus 2i is an abbreviation for negative 1 plus negative 2 times I. As a point, we have negative 1, negative 2, and we move left negative 1 and down negative 2 to plot that point. The x-axis is also known as the real axis, and the y-axis is also known as the imaginary axis. Where the two axes intersect is called the origin, and as a point, that's the point 0, 0. As a complex number, 0 plus 0i. The first example we did 2, or 2 plus 0i, is an example of a real number. The second example, I, or 0 plus 1i, is an example of a pure imaginary number. We can also visualize the complex number z equals a plus bi as a directed line segment, or vector, starting at the origin and ending at the point AB. Let's look at a couple of examples here. We have the point 1, 2, or the vector 1 plus 2i. Notice how we draw an arrow starting at the origin and ending at the point 1, 2. The complex number 2 can be visualized as an arrow starting at 0 and ending at 2 on the x-axis. And I can be visualized as an arrow starting at 0 and pointing straight up, ending at 1 on the y-axis. In the complex number z equals a plus bi, a can be written as RE of z for the real part of z, and b can be written as IM z for the imaginary part of z. Two complex numbers are equal if and only if they have the same real part and the same imaginary part. Symbolically, a plus bi is equal to c plus di if and only if a equals c and b equals d. We add two complex numbers by simply adding their real parts and adding their imaginary parts. So a plus bi plus c plus di is a plus c plus b plus d times I. We can visualize this sum as the vector starting at the origin, that is the diagonal of the parallelogram formed from the vectors a plus bi and c plus di. Let's look at an example. 1 plus 2i plus negative 3 plus I. Using the formula, we get negative 2 plus 3i, because 1 plus negative 3 is negative 2, and 2 plus 1 is 3. Visually, we look at the vectors 1 plus 2i and negative 3 plus I, and then we draw two more vectors, a copy of each of those parallel to them. You could see those with dotted lines, dotted arrows, to form a parallelogram. And then we draw the vector starting at the origin and ending at the far vertex of that parallelogram to get the sum, which is negative 2 plus 3i. We multiply two complex numbers as follows. A plus bi times c plus di is ac minus bd plus ad plus bc times I. So the definition of multiplication is quite a bit more complicated than the definition of addition. But in just a little bit, we'll show you a way you can multiply complex numbers without having to memorize this formula. Let's look at an example. I squared is an abbreviation for I times I, which in turn is an abbreviation for 0 plus 1i times 0 plus 1i. Using the definition that I just gave you, we get 0 times 0 minus 1 times 1 plus 0 times 1 plus 1 times 0 times I. Simplifying a bit, we get 0 minus 1 plus 0 plus 0i, or negative 1 plus 0i, which we could abbreviate simply as negative 1. So we see that I squared is equal to negative 1 using this definition of multiplication. The following note will allow us to multiply complex numbers without having to memorize this formula. We can find the product of two complex numbers by using field properties and replacing I squared by negative 1. So a plus bi times c plus di, using left distributivity, we have a plus bi times c plus a plus bi times di. Then using right distributivity, we get AC plus BCI plus ADI plus BDI squared. Note that we also use some associativity and commutativity there as well. Okay, now we just replace I squared by negative 1. And then I'm going to group BCI and ADI as BC plus AD times I using right distributivity. And we're rewriting BD times negative 1 as minus BD. So that's equal to AC minus BD plus AD plus BC I as we already knew from the definition. Okay, I'm just going to write the definitions of addition and multiplication so we have them in front of us. And let's do one more example. Let z equal 2 minus 3i and w equal negative 1 plus 5i. Z plus w is 2 minus 3i plus negative 1 plus 5i, which is 2 plus negative 1 plus negative 3 plus 5 times I, or 1 plus 2i. Z times w is 2 minus 3i times negative 1 plus 5i, which is 2 times negative 1 minus negative 3 times 5 plus 2 times 5 plus negative 3 times negative 1i. That's negative 2 plus 15 plus 10 plus 3i, which is 13 plus 13i. Theorem. The set of complex numbers, together with the operations of addition and multiplication, is a field. Let's just recall for a moment the definition of a field. So a field is a triple f plus times, where f is a set, and plus and times are binary operations on f, satisfying, well, the first 5 conditions, closure, associativity, commutativity, identity, and inverse for addition in the field F, tell us that we have a commutative group under addition. The next 5 properties, closure, associativity, commutativity, identity, and inverse for multiplication in F star, tell us that we have a commutative group under multiplication, but only when we restrict to F star, the non-zero elements of the field. And the last 2 properties are distributivity, and we have to have that 0 and 1 are different from each other. As an example, we're going to prove the commutativity for addition. Okay, so commutativity for addition says for all x, y in a field, x plus y is equal to y plus x. Okay, so here's the proof that addition is commutative in the complex numbers. Let a plus bi and c plus di be complex numbers. Then a, b, c, and d are real numbers. Now, since the set of real numbers together with addition and multiplication is a field, addition is commutative in the set of real numbers. So a plus c is equal to c plus a, and b plus d is equal to d plus a. Therefore, a plus bi plus c plus di, by definition of addition of complex numbers, is a plus c plus b plus d times I. Using the commutativity of addition in the reals, we could rewrite that as c plus a plus d plus bi. And then using the definition once again, that's c plus di plus a plus bi. Okay, so since a plus bi and c plus di were arbitrary complex numbers, we see that addition is commutative in the complex numbers. As an exercise, you should check the other 11 field properties. And here are some useful notes that will help as you go through them. The identity for addition is 0, or 0 plus 0i. The identity for multiplication is 1, or 1 plus 0i. The additive inverse of z equals a plus bi is negative z equals the negative of a plus bi, which can be written as negative a minus bi. And the multiplicative inverse of z equals a plus bi is z inverse equals a over a squared plus b squared minus b over a squared plus b squared times I. Let's define subtraction. If z and w are complex numbers with z equal a plus bi and w equals c plus di, then we define the difference z minus w by z minus w equals z plus the negative of w, which is a plus bi plus negative c minus di, which is a minus c plus b minus di. Let's look at an example. 1 plus 2i minus 2 minus I. According to definition, that's negative 1 plus 3i. Here's a picture showing the complex numbers as vectors, 2 minus I and 1 plus 2i. We can visualize this subtraction by first replacing 2 minus I by negative 2 plus I, so that we could change the subtraction problem to the addition problem, 1 plus 2i plus negative 2 plus I. Okay, so that vector, negative 2 plus I, it has the same length as 2 minus I, but points in the opposite direction. We then form a parallelogram using 1 plus 2i and negative 2 plus I as edges, as we would normally do for addition. And finally, we draw the diagonal of that parallelogram to see the result. And there we have negative 1 plus 3i. Let's define division. If z is a complex number and W is a non-zero complex number with Z equal A plus BI and W equals C plus DI, then we define the quotient Z over W by Z over W is equal to Z times W inverse. So Z is A plus BI. The inverse of W is C over C squared plus D squared minus D over C squared plus D squared times I. And using the definition of multiplication, we get AC plus BD over C squared plus D squared plus BC minus AD over C squared plus D squared times I. The definition of division in a field unfortunately led to a messy looking formula. However, when actually performing division, there's actually an easier way. We're going to use conjugates instead. The conjugate of the complex number Z equals A plus BI is the complex number Z bar equals A minus BI. Let's look at an example. Let Z equal 2 minus 3i and W equal negative 1 plus 5i. Then Z bar is 2 plus 3i and W bar is negative 1 minus 5i. Let's find the quotient Z over W using these conjugates. What we do is we multiply the top and bottom of the fraction by the conjugate of W, conjugate of the denominator. So we have 2 minus 3i times negative 1 minus 5i over negative 1 plus 5i times negative 1 minus 5i. On top, we get negative 2 minus 15 plus negative 10 plus 3 times I. And on the bottom, we get negative 1 times negative 1, or negative 1 squared, plus 5 times negative 5i squared, which is 5 times 5, or 5 squared. And that simplifies to negative 17 minus 7i over 1 plus 25, which is negative 17 over 26 minus 7 over 26 times I. Note that the product of a complex number with its conjugate is always a non-negative real number. Specifically, if Z equals A plus BI, then Z times Z bar is A plus BI times A minus BI, which is A squared plus B squared plus negative AB plus AB times I, which is just A squared plus B squared. That's a non-negative real number. So if Z is equal to A plus BI and W is C plus DI, then we have Z over W. Using the same trick as in the example, we're going to multiply top and bottom by the conjugate of W. So we get A plus BI times C minus DI over C plus DI times C minus DI, which is AC plus BD plus BC minus AD times I over C squared plus D squared. That's AC plus BD over C squared plus D squared plus BC minus AD over C squared plus D squared times I. Notice that we get the same expression as in the original way we defined it above. So one question you might be asking yourself is, can we put an ordering on the field of complex numbers so that we get an ordered field? By this next theorem, the answer is no. The field of complex numbers cannot be ordered. So before we jump into the proof, let's just remember what an ordered field is. Recall from lesson 5 that in an ordered field, we have the following 3 properties. If A is positive and B is positive, then A plus B is positive. That's order property 1. If A is positive and B is positive, then A times B is positive. That's order property 2. And 3, for every element A, exactly one of the following holds. A is positive, A is 0, or A is negative. And by A being negative, we mean that negative A is positive. Okay, let's prove this. Suppose toward contradiction that less than is an ordering of the field of complex numbers. If I is positive, then negative 1, which is I squared, that's an abbreviation for I times I, that must be positive by order property 2. If I is less than 0, then negative I is greater than 0. And therefore, negative 1, which is I squared, is negative 1 times I, which is negative 1I times negative 1I, which is negative I times negative I, must be positive. Again, by order property 2. So -1 is definitely positive. And it follows that 1, which is -1 times -1, is also positive, again, by order property 2. Therefore, we have -1 positive and 1 positive, violating order property 3. So the field of complex numbers cannot be ordered.